In this video, we will discuss electric potential energy and electric potential. Conservative forces are forces where the work done by the force is independent of the path taken. For such conservative forces, we can derive potential energies, such as gravitational potential energy for the force of gravity, and electric potential energy for the electrostatic force. Because of work-energy equivalence, we can measure the change in potential energy relative to work done. As it is an energy quantity, we measure it in joules. Electric potential is the electric potential energy per unit charge, similar to how the electric field is the electric force per unit charge. It's generally more convenient to use. We can measure the difference in electric potential between 2 points. We measure electric potential in volts. Electric potential energy and electric potential are inversely proportional to the distance from the charge. So, as you get closer and closer to a charge, the potential and potential energy will approach infinity. Similarly, as you get further away from the charge, the potential will decrease to zero. For negative charges, the same is true. However, negative potential is attained instead of positive potential. As you get closer to a negative charge, you approach negative infinity potential and negative infinity potential energy. Say we have two charges of equal magnitude but opposite sign in close proximity of each other. Were we to plot the potential in the field around these charges, we would get a steep slope moving from the positive charge to the negative charge. Charges, thus, will want to move from areas of high potential to low potential. For point charges, we can calculate potential energy between the charges. We will assume that two charges will have zero potential energy when they are infinitely far away from each other. Similarly, we can calculate electric potential due to a single point charge at a point in space near the charge. Again, we will assume that being an infinite distance away from the charge means that we have zero electric potential. In our first example, a proton is located at a point A in an electric field with an electric potential energy of 3.2 times 10 to the negative 19th joules. It then moves to point B, 1 times 10 to the minus 10th meters to the right. We would like to know what its electric potential energy is at point B, if the force it experiences is 0.8 times 10 to the minus 9th newtons to the right. We can calculate the change in electric potential energy as the negative of the work done. Similarly, we can say that the electric potential energy at the final position, point B, is the negative work plus the electric potential energy at point A, the starting point. We are moving the charge in the direction of the force. Thus, we should expect to have a decrease in electric potential energy of the charge. With this in mind, we can first calculate the work done moving the charge from point A to point B. This is equal to the force times the displacement of the charge. The force is 0.8 times 10 to the minus 9th newtons, as was given to us, and the displacement is 1 times 10 to the minus 10th meters, also given to us. Multiplying, we have a resulting work done of 0.8 times 10 to the minus 19th joules. Taking the negative of this and adding it to our initial electric potential energy, we have an electric potential energy at point B of 2.4 times 10 to the minus 19th joules. Because we started with 3.2 times 10 to the minus 19th joules and ended with 2.4 times 10 to the minus 19th joules, we have decreased the electric potential energy, which is what we expected to happen. In our second example, we have an electron, and we'd like to measure the potential difference between 2 points, one point being 1 times 10 to the minus 10th meters away, and another point being 5 times 10 to the minus 10th meters away from the electron. We can measure the electric potential due to a point charge, but if we would like to measure the change in potential between 2 points, we modify the formula a bit to account for two different distances. Here, we're moving further away from a negative charge, so the potential should increase from a more negative number to a number closer to zero. Plugging our numbers into this equation, we have 8.99 times 10 to the 9th Newton meters squared per coulomb squared, times the magnitude of the charge, negative 1.6 times 10 to the minus 19th coulombs, times 1 over 5 times 10 to the minus 10th meters, minus 1 over 1 times 10 to the minus 10th meters. Multiplying out and calculating, the potential difference is 11.5 volts. Our potential difference, 11.5 volts, is positive, so this is an increase in potential. The potential at point B is greater than that at point A.